Good morning. Today we look at examples for chapter 5. So let's make this kind of like an in-class problem solving. So take your calculators out and you're going to go ahead and solve this, and then I'll guide you as we go along. Okay. So there are first two problems where we learn about sinusoidal waveforms, how to combine voltages and currents that are in sinusoidal waveforms. Then we'll look at examples for inductor and current, and then we'll build off all four examples and solve one large circuit in example number 5. So probably won't be able to get to 5 today, but I want to cover at least the first 4. So okay. All right, examples 1 and 2 simply states voltage Vs of t is 10 cos omega t plus 10 sine omega t. Okay. Your job is to combine both of them together and find an expression for Vs of t. Find an expression for Vs of t. So the first thing about adding or subtracting two sinusoidal waveforms is that their frequency must be the same. If the frequency is not the same, you cannot add or subtract them. Okay. So basically, if you have like two audio signals, both of them running at different frequencies, and you try to add or subtract them, it's not going to work. Okay. So that's the first thing. And that's the most important point. So to add, subtract sinusoidal waveforms, or functions, the frequency must be the same. That's the first thing you should note. So in this example, frequency is not given to us, simply stated as variable omega. We don't really care what the value is, because when we add two phasors together, omega is irrelevant, right? And so all we need to do is ensure that both the frequencies are the same. In this case, it is omega for both of them, so they are the same. So it is possible to add them together. Okay. So the steps involved in this, again, is mathematical, right? You're taking two voltages. It could be two currents, doesn't really matter. Two sinusoidal waveforms, and you're adding them up. So the first step we do is we're going to convert them into their phasor form. To convert them into a phasor form, the waveform needs to be in cosine. So go ahead and change the sine waveform to cosine. Sine x is equal to cos of x minus 90. So this is 10 cos omega t plus 10 sine omega t. In order to write the phasors, you change that to cosine. So this becomes 10 cos of omega t minus 90. Now go ahead and write out the phasors for both. To write the phasor, you need the magnitude and the phase angle. Write the phasor for both and perform the calculation. Let me know what answer you get. Ask questions. If you have any concerns, if you need to clarify anything. So what do we have? Anyone? What's the phasor for the first one? 10 with an angle 0. How about the second one? 10 negative 90. Yep. So perform this operation on your calculators, online solvers, MATLAB, however you want to do it. And then let's check your answers, see if they all match up. So phasor VS will be 10 angle 0 plus 10 with the angle of minus 90. Perform this calculation. Now, as I said, if you have programmable calculators, you can program this directly and you'd be able to obtain a magnitude and a phase angle. I don't. And so what I would do is, and this is also the approach the book takes, because this is how engineers used to solve them, right? So engineers, as training engineers or trainee engineers, you should be aware of how this is solved without a calculator. So I would convert this to rectangular coordinates because I'm performing an addition, right? So 10 with an angle 0 becomes 10 plus J0. And 10 with an angle of minus 90 becomes 0 minus J10. Now, if you're thinking how this come about, it's basically a right angle triangle. So a phasor that is 10 with an angle 0 is lying on the real axis. And this is the imaginary axis. And so the rectangular coordinates are simply 10, and there is no imaginary value because there is no angle. So it's 10 plus J0. This is 10 plus J0. And then a vector which has a magnitude of 10 and lies at a 90-degree angle, 90 degrees, or it's actually minus 90. Minus 90 means it's going clockwise. And so this is minus 90. Magnitude of 10 with an angle of minus 90, meaning the real component is 0, imaginary is minus 10. And hence, 10 with an angle of minus 90 becomes 0 minus J10. Does that make sense to everyone? Right? Again, as I said, more often than not, you will have calculators and software tools at your disposal. And so if they are available to you, you can use those tools. But as engineers, you should be aware of how this comes about. So does anyone have the final answer? Yes, that's from here, but we need the answer in time domain because we are asked to find the value of Vs as a function of time. So final answer will also be in cosine. We have to perform an inverse phasor transform. And so in this case, since it's 10 minus J10, we will transform it into polar coordinates. And that's the answer I'm asking for. Okay, so one student has an answer as 14.14 magnitude and an angle of minus 45. Anyone else? I got one more thumbs up. That's it, only 2 students. No one else wants to solve this. All right, 14.14 with an angle of minus 45. And so Vs of t is 14.14 cos of omega t minus 45 volts. That should be your final answer. If voltage or current is asked as a function of time, then your final answer should be in this cosine form. When you perform the inverse transform, you would simply take the magnitude, meaning 14.14 from the vector, and you take the phase angle, minus 45. The frequency does not change. Okay. Inductors, capacitors, and resistors do not affect the frequency. They only affect the magnitude and they affect the phase. They do not affect the frequency. So if they don't affect the frequency, that frequency remains the same. You simply take it from your input. The input had omega t, your output also has omega t. All right, questions? Yeah. When we add them, that's the answer we obtain. Graphically, if you try to add these together, you have a vector here, you have a vector here, right? This is 10 plus J0. This is 0 minus J10. If you add them together, you get this. So it's minus 45. And then the length of this vector is 14.14. Yeah. Yep. That's how it comes about. Okay. Any other questions? All right. Let's look at the second one then. Sample 2. We have again 20 cos omega t minus 45, and again a sine wave function. So go ahead and convert that to cosine. Vs of t is 20 cos omega t minus 45 plus V2 of t, which is 10 sine omega t plus 60. First step, is the frequency the same? Yes, it is. It's simply omega t. So it is possible to add or subtract these two waveforms. Then the next step is convert everything to cosine. One of them is cosine, the other one is not. So we subtract 90 degrees from that waveform. So this becomes 20 cos omega t minus 45 plus 10 cos of omega t minus 30. Write down the phasors and perform the calculation. What do you get? Magnitude and phase, and you perform this calculation. Magnitude, resulting magnitude. In the meantime, I will convert this. Anyone? Final resulting magnitude. Okay, 29.77. That is correct. How about the angle? -40. Yes, that is correct. Again, every student needs to be adept at making these calculations.
Professor, I have a question.
Yes.
So on a test or on a quiz, if we're able to just perform the calculations on our calculator, do you still want us to write down all the processes like that?
No. So the question being asked is, do you have to show all the intermediate steps? The answer is no. You can go directly from, let's say, from this step to this step.
Okay, thank you.
Direct answer from calculator. The only thing I would state or advise is you have to ensure that you're an expert at doing these calculations, because if you make an error entering the equation, then your final answer would be incorrect. And so if a student goes directly from, let's say, setting up the equation to the final answer without any intermediate steps, I would not be able to award partial credit. So again, this is an important point I make. So even without this question, this was going to be my next point. It's like you can skip the steps and write out the final answer, but you better be confident in your abilities, because if you make an error, I would not be able to award partial credit in the middle. Okay. So if you do show the steps in the middle and your final answer is incorrect, I would still be able to give you partial credit for the steps that are correct. Yes. So in which one? No, we always keep it in degrees. We don't change it to radians. So the question being asked is, should we change it to radians? The answer is no. We always keep it separate in degrees. Okay, not in radians. Again, because so there are something known as phasor diagrams. And so we plot these phasors. And when we plot the phasors, we want to know exactly which angle we're talking about. Obviously, we can do it at radians too, but it's easier with degrees. All right, other questions? Is the process clear? Is the process clear? Okay, a real life application of adding or subtracting sinusoidal waveforms is in noise canceling headphones. So in noise canceling headphones, what it does is there are microphones, and every phone has this feature. So the noise cancellation feature, what it does is there's a microphone near the speaker, right? There's a microphone near the speaker, and it captures the sound wave around the speaker, surrounding sound waves. Then it inverts the phase by 180 degrees. Equal magnitude, opposite phase. When you add the waveforms, if you add a waveform like this and you invert the magnitude, turns out to be 0. So if there are surrounding noise, the microphone captures that noise, inverts the phase 180 degrees, adds it together, and so the surrounding noise is basically canceled out. You don't hear it in your speakers. That is a real life application of where you would add these kind of sinusoidal waveforms. Okay, noise cancellation. Okay, let's go to examples 3 and 4. We have 15 minutes. I think we should be able to get through these. So the first two, we looked at examples 1 and 2, look at sources. Example 3 and 4 looks at components. Resistors behave exactly the same way. So we don't, we are not focused on resistors as much. We are focused on inductors and capacitors. Now, if you think back to chapter 3, finding the voltage or the current for inductor capacitor, we'd have to differentiate or perform integration. Here, we can apply simple Ohm's law. Circuit's not given to us, but what is given is that you have an inductor value, voltage for the inductor, VL of t, that is being applied or appears across the inductor. And we are asked to find IL of t. This is a mistake. VL of t is already given to us. We don't need to find it again. And so it's the same case, the second one. Okay, so inductor value is given, inductor voltage is given. We're asked to find the current. Okay, again, inductor voltage, VL is L di over dt. If we wish to find the current, we would integrate the voltage. In this case, we don't need to do any of that. Simply apply Ohm's law by changing the math, complex numbers or complex math. Okay, so example 3, we have our expression VL of t is 100 cos of 200t. So the steps for this, of course, is we need Ohm's law, right? We find current through Ohm's law. V equals IZ. We are given V, we are given the value of L. From the value of L and from the omega value in V, we can determine Z, impedance, and then we can apply Ohm's law. So that's the method and the procedure for both examples, examples 3 and 4. So first thing is you take the standard expression, which is V of t is Vm cos omega t plus theta, and you extract the 3 key pieces of information: magnitude of the voltage, the omega value, angular frequency, and the phase. Okay, so in this case, Vm magnitude or the V peak is 100 volts. Omega is 200 radians per second, and phase angle theta is 0 degrees. You take the standard expression and you compare it to the given value of the voltage or the current, and you extract the 3 values: peak or magnitude, angular frequency, and the phase. Once you have omega, you can apply the equation for ZL, which is J omega L. And J omega L gives you J times 200 times 0.25 Henry, which is 50. Or J50. Also, this is in rectangular coordinates. J omega L is rectangular coordinates. But I need to perform a division. Right? V equals IZ. I is V over Z. So I want the answer for impedance Z in the polar form, in polar coordinates. And ZL in polar coordinates is omega L with an angle of plus 90. Standard equation, omega L with an angle of plus 90. You get the same answer, 200.25. You get 50. With an angle of plus 90. Remember, for an inductor, the impedance is always plus 90. For a capacitor, it's always minus 90. And once you have this, apply Ohm's law. A phasor for VL. You can find that directly here. magnitude 100, phase angle 0. Magnitudes get divided. So 100 divided by 50 gives me 2. And phase angles get subtracted. So VL over ZL, VL is magnitude 100 divided by magnitude of impedance 50 gives me a value of 2 amps, and the phase angle 0 minus 90, so phase angle of minus 90. Now, we are asked to find IL as a function of time. So your final answer has to be as a function of time. So IL of t is 2 cos of 200t minus 90. Let's take a pause. You write it down. Let me know if you have any questions. If you understood this, then you move forward with example number 4. Yes. So here. So the question being asked is, do we have to convert it to polar? I think that's the essence of your question. The answer is not really. If your calculator can perform a division with rectangular coordinates and polar coordinates together, then it's fine. You can simply go ahead and do that. And I think most programmable calculators which students have nowadays can do that. So you would not need to do a manual conversion. So again, the question being asked is, do we have to convert it to polar form from rectangular? The answer is no. Yes. No, it's a complex quantity. Impedance is a complex quantity. So the question being asked is, for impedance ZL, can we just leave it as magnitude? The answer is no. It's not, because if we say just J50, J50 is the imaginary portion. It's not the real portion, meaning it only has a reactance, but there is no resistance in there. And so it would not be just the magnitude. Yes. Typically, it's always before the number. But I think you know what? Actually, I've never seen where it's no 50. I have seen where it comes afterwards also. Yeah. All right. Any other questions? Okay, go ahead and solve example number 4. It's exactly the same. I will go ahead and solve along with you. But again, as good practice, you might want to not look at my screen or my work. Go ahead and solve it and then verify your answers. So example 4. Impedance of a capacitor is 1 over j omega c, or 1 over omega c with the angle of minus 90. The final answer obtained was magnitude of 2 and phase angle of plus 90. Let me know if that's not what you obtained. And let me know if you have any questions. Any questions? Yes. Because the current always lags. So not current lags, current always ahead, voltage lags, because the voltage cannot change instantaneously, so it changes 90 degrees. So it's always 90 degrees behind the capacitor current. So when you do the impedance, it always is minus 90. Yes. Yeah. You can try and solve it that way and it should come out. Yeah. So one final thing, example 5, we'll look at on Wednesday. Just wanted to point out that 1 over j, does everyone know why 1 over j is minus j? Multiplied by j, but yeah, small derivation. 1 over j can be j over j. That gives you j over j square, hence minus j. So when you have capacitor 1 over j omega c, the vector form, polar coordinates, is reflected in minus 90 degrees, and as j then becomes minus j. All right. Have a good day. I'll be in my office later this afternoon. If you have any questions, stop by, and then I'll see you all on Wednesday.